Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Time Dependent Non-Newtonian Fluids and Viscoelastic Non-Newtonian Fluids. Now, before going into the details of today's lecture, we will be having a recapitulation of what we have studied till now. In previous couple of lectures, what we have seen several characteristics of Newtonian fluids and then making those characteristics of Newtonian fluids as a kind of base to define non-Newtonian fluids, and then based on the different possibilities of non-Newtonian fluids, we have classified them into three different categories. One category is time independent non-Newtonian fluids, another category is time dependent non-Newtonian fluids, and then third category is the viscoelastic non-Newtonian fluids, right. So, in the previous lecture what we have seen a in detail discussion, we had in detail discussion about time independent non-Newtonian fluids and then subclassification of those time independent non-Newtonian fluids, models for those time independent non-Newtonian fluids. That is what we have seen, that is for a shear thinning, viscoplastic and shear thickening type of time independent non-Newtonian fluids. We have seen almost all possible details in the previous lecture. Now, in today's lecture, we will be discussing a few details about time dependent non-Newtonian fluids and then viscoelastic non-Newtonian fluids. So, but before going into the details of time dependent non-Newtonian fluids, what we will be doing, we will be having a few problems on time independent non-Newtonian fluids, because in the previous lecture we could not have a time to discuss example problems. So, now we see a few example problems on time independent non-Newtonian fluids before going into the time dependent non-Newtonian fluids. So, the first problem on time independent non-Newtonian fluids is as follows. Following shear stress versus shear rate data are available for aqueous carbapol solution at 293 Kelvin. By plotting these data on linear and logarithmic scales, ascertain the type of fluid behavior of this solution, suggest a suitable viscosity model and evaluate parameters of this solutions, rheological parameters of this solution. That is the question, and then data shear stress versus shear rate data is given here, that is here. Shear rate is given in second inverse, shear stress is given in pascals. So, what we have to do, this experimental data whatever is there, that we have to first plot, we have to plot on linear scale, so that when you have this shear stress versus shear rate curve, then you can come to know whether this data is linear or non-linear. Is it passing through the origin or is it not passing through the origin? If it is not passing through the origin, then again is it linear or non-linear after crossing that yield stress point. So, all those things we can come to know only when you draw this shear stress versus shear rate information, right. So, first that we will do, and then we are also asked to make a logarithmic scale. Logarithmic scale plotting also we have to do, that is we have to take log of shear stress and then we have to take log of shear rate and then we have to plot them log of shear stress versus log of shear rate, or straightforward on a log graph sheet you can plot shear stress versus shear rate as a second part of the question. Then from the first part of the question, when you plot this shear stress versus shear rate data on a linear scale, then based on that one we have to ascertain which type of fluid is it a Newtonian or non-Newtonian. If it is non-Newtonian, what type of non-Newtonian fluid, that we can know from the linear plot of shear stress versus shear rate on a linear scale. So, that is what we do. Once we realize that if it is non-Newtonian fluid, so then which type of non-Newtonian fluid, that we can realize from the plot of shear stress versus shear rate, then we can do accordingly simple calculations to obtain the modal parameters. Okay. So, this is the given data once again redrawn here. So, now the shear stress versus shear rate data, first we will have to plot on a linear scale. So, when you plot in the shear stress versus shear rate on a linear scale, so then what you can see, it is not passing through origin obviously, and then after that it is having a non-linear curve like this. Okay. So, that is what I have done on Excel sheet. We can do on a normal graph sheet using pencil and pencil like this. So, then we get this curve like this. So, then what is this curve? This curve is obviously what indicates, if you extrapolate it to this x is equals to 0 line, that is gamma dot is equals to 0. So, then you get corresponding value of yield stress. That clearly we can see that when gamma dot is 0, shear stress is not 0. So, obviously, it is not a kind of a Newtonian fluid, and then it is not a kind of a power law fluid or a shear thinning or shear thickening fluid. It is a viscoplastic fluid because it is having some yield stress, right. So, that is what we understand. So, now since we have done in Excel sheet, so directly we can understand. So, it is a after crossing this yield stress point, whatever the behavior of this curve is there, that can be well represented by power law model with n is equals to 0.2086 and then m is equals to 74.149 or something like this. But however, in exams we may not be having the Microsoft Excel to plot directly. So, then what we do, we have to have a kind of alternative approach of calculating them. Okay. So, now from here what we understand, this fluid has a viscoplastic behavior, and then that also Herschel-Bulkley fluid behavior. Why Herschel-Bulkley fluid behavior? Because after crossing this yield stress, it is having a non-linear curve like this shown it. After crossing this yield stress, if it is linear, then it is a Bingham plastic. Since it is not linear after crossing this yield stress, it is Herschel-Bulkley fluid or yield plastico fluid, right. So, now extrapolate this curve to 0 shear rate value to get a yield stress value, and then that is 47 pascals. That is 47 pascals is your tau naught h. Right, you know that tau yx is equals to tau naught h plus m gamma dot yx power n for Herschel-Bulkley fluid. So, now at least by having this shear stress versus shear rate curve on a linear scale, so then we realize that it is Herschel-Bulkley fluid. So, then second part of the question is that we have to find out the modal parameters, and then there are 3 parameters. Out of 3, one you already got it, tau naught h, right, as a 47 Pascal. So, now m and n you have to find out, right. We can find it out, find out that one as well. So, now what we do, next part of the question is that we have to plot this data on a log scale as well. So, what I have done, rather taking the log graph sheet, I have taken log of shear rate versus log of shear stress, whatever the shear rate, shear stress information is given. So, that I have taken into the, I have converted into the log of shear rate and then log of shear stress corresponding respectively, and then I have plotted them. So, log of shear stress versus log of shear rate. Then if I plot this data, what I get a straight line. So, I get a straight line. So, that what I am here doing is that I am not taking the tau naught h value into the consideration, remaining values only I am taking. So, remaining part is having power law behavior kind of thing. So, if you exclude the tau naught h, this is what you are having, right. So, then from if you take the log of either side, so then you will get whatever this m and n values. So, from here intercept is nothing but log of m, and then slope is nothing but n. Okay. Slope is 0.2086 that you are getting, intercept log of m, that is 1.8701 you are getting. From here m you will get around 74 point something like this. So, that you can clearly get. So, then rheological parameters you can find out n, the slope of this log of shear stress versus shear rate curve, that is nothing but 0.2086, and then intercept is nothing but log of m, that is 1.8701. So, that is m is equals to 74.148 Pascal second power n, right. This is how we can do. So, very simple, straightforward. So, we take another example problem. Following steady shear data has been reported for a polymer solution at 298 Kelvin. So, gamma dot is given in second inverse, tau is given in Pascal, right. The question is, evaluate the modal parameters for the following viscosity equations, power law model and then Bingham plastic model. In the previous question, it has not been mentioned which model you have to do the curve fitting for that given shear stress versus shear rate data. But now here it has been given, like we have to fit this data using the power law model and Bingham plastic model. Okay. So, first we do the power law model curve fitting. So, this power law model, what you get, tau yx is equals to m gamma dot yx power n. So, if you take log either side, log of tau yx is equals to log of m plus n log of gamma dot yx, this is what you have. So, now if you plot log of tau yx versus log of gamma dot yx, then you will get a straight line of slope n and then intercept log of m. So, first we have to do the curve fitting using the power law model. So, whatever the data shear stress versus shear rate data is there, so this is the given data, we have to apply the trend line of power law behavior, and then is it really replicating or not, that is what we have to see. So, it is anyway, it is fine. Okay. So, so what you get from directly, if you are doing Excel directly, you are getting this m, this n, and then this m values directly you are getting, right. But if you wanted to do using graph sheet and pencil, so then you have to do it, you have to plot it on the log graph sheet or convert the data in log of shear rate and then log of shear stress like that, and then you plot them in a linear scales, okay, linear graph sheet you can plot. So, then when you convert this data into the log terms like log of shear rate and a log of shear stress, then you plot it. So, then you have a straight line like this, which is having a slope of 0.1594 and then which is having a intercept of 1.8016. So, n is equals to 0.1594 and then m is equals to 63.33 Pascal second power n, right. So, next part is that the same data we have to fit using Bingham model curve fitting. So, Bingham model curve fitting, what we have, tau yx is equals to tau naught h plus mu b gamma dot yx, that is it. So, if you plot it linearly, you get a straight line like this. So, then tau naught b, this is not tau naught h, tau naught b, because we are doing for the Bingham plastic model. So, that you get approximately 50.427 and then viscosity mu b you get 10.436. So, 50.43 Pascal is tau naught b yield stress, and then Bingham viscosity, that is mu b is equals to 10.44 Pascal seconds. So, you can see here the curve fitting is not very good, 96% only, R square is 0.96 only, but other case R square is almost like 0.99, but again there also we are not taking the yield stress point anyway. So, example problem number 3, the rheological properties of a China clay suspension can be approximated by either a power law or a Bingham plastic model over the shear rate range of 10 to 100 second inverse. If the yield stress is 15 pascals and the plastic viscosity is 150 millipascal second, what will be the approximate values of the power law consistency coefficient and then flow behavior index? So, now for you the data is given like tau naught b is given and then mu b is given 150 millipascal second. So, 150 into 10 power minus 3 Pascal second, okay. And then gamma dot range is given, one is 10, another one is 100. Between these two ranges only this information is valid, okay. So, now we know this tau yx is equals to tau naught b plus mu b gamma dot yx. So, gamma dot yx is 10. So, what is the corresponding tau yx, you can find out from this equation, because tau naught b is given and then mu b is given. Similarly, when gamma dot yx is 100, what is the value of tau yx? So, that is what you get. So, then so now you get this information. So, then next model parameters you can find out, okay. So, before going into the solution, one important thing that you have to understand is that this is the curve fitting, right. So, for this whatever the China clay suspension is there, already tau versus gamma dot information has been obtained, right, between 10 to 100 second inverse of shear rate. Of course, tau information is not given, rather giving tau information it is given when that information tau versus gamma dot x is plotted using Bingham plastic model, right. So, whatever the tau versus gamma dot information is there, that has been plotted using the Bingham plastic model, and then whatever this tau naught b is there, that is given, right, and then slope of this curve mu b, how much, that is given, right. So, now what you have, now this is, let us say 10, 100, this is 0 anyway. So, this values of shear rate are given, right. So, corresponding this information you have to find out, that you can find out by using this equation. So, whether you are doing the curve fitting using the Bingham plastic model or power law model, this tau versus gamma dot information is not changing, that is experimental information. So, now rather fitting like this curve, what you are doing, you are fitting like in a different way, using a power law model you are fitting. So, now same data if you are fitting using the power law behavior, so then let us say you may be getting data something like this, for example, for a power law model. Right. So, whether you are using this red color Bingham plastic curve fitting or this blue color power law curve fitting, your data tau versus gamma dot data is not changing, it is going to be same, it is going to be same, right. So, then that understanding is required. So, then once you have this thing, then corresponding tau information you can find out from the Bingham model, and then that same tau information you can use for the power law model to find out the m and n values. Okay. So, now that is how we will progress to solve this problem. So, for Bingham plastic model, tau y x is equals to tau naught h plus mu b minus dvx by dy, and then minus dvx by dy, lower limit is 10. So, when it is 10, tau y x is equals to tau naught b is 15, and then mu b is 150 millipascal second, and then this gamma dot y x shear rate is nothing but 10 second inverse. So, when you substitute all this, you will get 16.5 pascals. Then similarly, other limit of gamma dot y x is 100 second inverse. So, when it is 100, tau y x is how much? Tau naught b is remaining same anyway, mu b will also remain same, only this in place of gamma dot y x you will be substituting 100. So, then you will get 30 pascals. So, now when you have this information gamma dot y x, tau y x when it is 10, tau y x is 16.5, when it is 100, this tau y x is 30. So, now power law model tau y x is equals to m gamma dot y x power n. So, now you have two data points, you need to you have a two unknowns. So, then you can get the two equations, let us say 16.5 is equals to m 10 power n, then 30 is equals to m 100 power n. You have two equations, two unknowns, you solve and then you get the solution. So, that is what we are going to do for power law model. Because same data if you are applying for the power law fluid or power law model, then what are the corresponding model parameters m and n that we have to find out. So, when gamma dot y x is 10, you get this equation 16.5 is equals to m 10 power n. When gamma dot y x is 100, then you get this equation 30 is equals to m multiplied by 100 power n. So, this tau y x we already found using the parameters given for the other model, Bingham plastic model, right. Then finally, if you solve these two equations, you will get n is equals to 0.26 and then m is equals to 9.08 Pascal second power n, right. This is how we have to solve the problems, simple and straightforward. Now, we see the details of time dependent fluid behavior. While categorizing or while classifying the non-Newtonian fluids, we have already seen these time dependent non-Newtonian fluids, the shear stress versus shear rate information whatever is there, that is also function of time. That is, duration of shearing is also going to affect the apparent viscosity of these fluids. So, if the duration with the duration of shearing, if the apparent viscosity is changing, then we call such kind of fluids are a time dependent fluid behavior, because with the time it is changing, the apparent viscosity is changing. So, the apparent viscosity depends on the rate of shear plus duration of shearing as well. Okay. So, then time dependent fluid rheology behavior estimation, how to do it? How do you find out whether the material is having time dependent rheological behavior or not? So, for that simply what you do the shearing experiment, okay, get the tau versus gamma dot information. How you do it? At a constant rate you increase the shear rate, and then let us say you get tau dot, let us say then tau versus gamma dot information you are getting like this. Now, after reaching certain higher shear rate, what you do? You should not change the rate at which you are changing the shear rate. You decrease the shear rate and then get the tau versus gamma dot information again. So, upper curve, this one is while increasing the shear rate at a constant rate, lower curve is the same tau versus gamma dot information for the same fluid, but decreasing the shear rate at the same rate. For the same fluid, using the same equipment at the same rate, we are increasing the shear rate and then we are decreasing the shear rate, but both the thing we are doing at the constant rate, at the same constant rate. We are not changing the rate at which you are changing the shear rate information, right. So, then when you plot these two curves, if both the curves, if these are superimposing, then you can say that there is no time dependent behavior. But if they are forming some hysteresis like this, so then that means it must be having some time dependent behavior. That is the reason when increasing and then decreasing, the time of shearing is changing, right. You are at a constant rate, you are increasing the shearing, and then you reach a maximum shear rate at a certain value, and then you are again at the same constant rate you are decreasing the shearing. So, the time parameter has come into the picture. So, but if both the times, if it is superimposing, tau versus gamma dot information is superimposing, then the material is time independent fluid rheologically fluid behavior. Rheological fluid behavior of the such material is time independent if they are superimposing. But if they are forming hysteresis like this, then it is having some time dependent behavior. You also may have something like this. Okay. You also may have something like this. Initially, you may have a kind of almost steady straight line, then again it may be having something like this. That is also possible. Whatever the nature of the curve, while increasing the shear rate and decreasing the shear rate, if they are forming hysteresis, then time dependent fluid behavior is existing, right. If they are not forming any hysteresis, then such materials rheologically time independent. Okay. Right. So, rheogram is measured by increasing shear rate steadily from 0 to some maximum value at a constant rate, that is very much important. Now, after reaching some maximum value of shear rate, rheogram is again measured by decreasing shear rate from that maximum value to 0 value, but at the same constant rate, Whatever rate you increase the shear rate to reach the maximum shear rate information or maximum shear rate value, at the same rate you have to decrease the shear rate to come back to 0 shear rate value. Then these rheograms, whatever the corresponding tau versus gamma dot information is there, that you have to plot, right. If these two rheograms exhibit hysteresis loop, then there exists time dependent nature of fluid behavior, right. If there exists a kind of hysteresis loop between these two rheograms while increasing the shear rate and then while decreasing the shear rate, then obviously the material is having time dependent rheological behavior. If they are superimposing, then the material is not having any time dependent rheological behavior. So, The height, shape and enclosed area of hysteresis depends on several parameters. Some of them are duration of shearing, right. How long are you doing the shearing? You are doing for 10 minutes or 10 hours or 100 minutes, that also makes a difference. And then rate at which increasing or decreasing of shear rate is taken place. At what rate you are increasing the shear rate or at what rate you are decreasing, or both are going to have a influence on the height, shape and enclosed area of the hysteresis. Then kinematic history of the fluids as well, playing a role on the height, shape and enclosed area of the hysteresis in the case of time dependent non-Newtonian fluids. So, obviously the larger the enclosed area, stronger is the time dependent behavior, right. Whatever this tau versus gamma dot information is there, if the hysteresis is having the larger gap, so then obviously the time dependent behavior is more if the gap is more here. Okay. If this the hysteresis is narrower, then we can say that the time dependent nature is weak, it is not very strong. For time independent fluids, no such hysteresis will form, and then two types of time dependent non-Newtonian fluids are possible. Obviously, what are the two? Is the apparent viscosity is increasing or decreasing with the duration of shearing, right. So, these are the two possibilities are existing. These are the two possibilities are existing. One is if the apparent viscosity is decreasing with the duration shearing, then we call them as thixotropic material. If the apparent viscosity is increasing with the duration of shearing, then we call them rheopectic or negative thixotropic materials. Now, we see a few details of these two as well now. But examples for this time dependent non-Newtonian fluids are laponite and bentonite clay suspensions, drilling fluids, waxy crude oils, red mud suspensions, cement paste, gypsum. Gypsum paste, you make a gypsum paste and then shake it well, and you make a gypsum paste and then keep it on a table on a container. So, then what happens? It resolidifies in larger time. Let us say the same container whatever in which you are taken the gypsum paste, and then what you do, you take in your palms and then rub like this. What happens? That may be resolidifying very quickly. That means with the duration of shearing, the gypsum paste apparent viscosity is increasing. It's a negative thixotropic material or rheopectic material. So, after shaking this gypsum paste, it resolidifies in 40 minutes if you keep it at rest, but it resolidifies within 20 seconds if the container is gently rolled in the palms. Okay. Now, rheogram of time dependent fluids, as I already mentioned, shear stress versus shear rate information you have to get for a increasing shear rate. Let us say increasing shear rate from 0 to some maximum value of shear rate you are increasing, right, but you are increasing at a constant rate and then reaching some maximum value of the shear rate, and then what you are doing next, you are decreasing the shear rate from that maximum value of shear rate to 0 value, but at the same rate as you increase the shear rate, but at the same rate. So, then now you can see you take this at this gamma dot value, you can see the shear stress is more while increasing shear rate, and then shear stress is less while decreasing the shear rate from maximum value to the 0 value. But both of them have been done, increasing and decreasing have been done at the same constant rate. So, the shear stress you can see they are very different from each other. So, while increasing the shear rate, the shear stress is having the larger value, while decreasing the shear rate, the shear stress is having the lower value for the same constant value of the shear rate. So, then apparent viscosity, which is obviously shear stress divided by the shear rate, right. So, that is decreasing. Initially it is having larger shear stress by same constant shear rate, then it is lower shear stress divided by the same constant at shear rate. Okay. So, apparent viscosity has decreased. So, they are thixotropic fluids may be having this kind of nature. whereas the other one, rheopectic material, when you are increasing the shear rate at a constant rate, you may have curve like this while reaching the maximum value of shear rate. Once reaching the maximum value of shear rate as per your requirement, decrease the shear rate again at the same rate to reach the 0 shear value, then you have this curve. So, now you can see here in this case, at this constant shear rate information, while increasing you have the lower value of shear stress, while decreasing you have the higher value of shear stress for the same shear rate value, That means apparent viscosity has increased for this material, and these are known as the rheopectic or negative thixotropic materials. So, one example we are taking here, proprietary body lotion. So, now here if you plot the apparent viscosity versus duration of shearing, you can see initially the viscosity has dropped suddenly to some lower value from approximately 50 Pascal second to approximately 10 Pascal second, right, as long as the duration of shearing is maintained up to something like 250, 200 to 250 seconds, and then you stop shearing. After stopping the shearing, you can see a kind of a build up of the structure of the material is taking place. So, then whatever the body lotion is there, its viscosity is increasing with when there is no shearing. This is one example of time dependent non-Newtonian fluids. Similarly, we have more examples we will be seeing, but we see in different categories within the thixotropy and then within the rheopectic categories we will be seeing these examples. So, thixotropy, apparent viscosity decreases with the time of shearing if sheared at constant rate, and then some examples are leponite and bentonite clay suspension, drilling fluids, waxy crude oils, red mud suspensions, and then cement paste. And then remember, some of these examples like drilling fluids, waxy crude oils, etc., you might have also seen in the other type of non-Newtonian fluids also in the previous lecture. But again I said that I already mentioned in previous couple of lectures that this nature of the non-Newtonian behavior, may be different under different different range of shear rate. So, this thixotropy you may be finding under certain different range of shear rate, whereas the same material may be displaying power law behavior under different range of shear rate. Okay. So, shear rate is very essential. However, these examples are generalized way they are provided. So, that is the reason shear rates are not provided here. Okay. So, that means the same fluid, drilling fluids may also show some viscoplastic behavior and they may also show thixotropic behavior as well. So, this cement paste, we can take a example. See, now cement paste, what we are doing, we are increasing the shear rate. So, when you are increasing the shear rate, so the curve is like this, shear stress versus shear rate curve is like this, right. We increase at certain constant rate. Now, at the same rate, we are decreasing the shear rate of this material. So, the corresponding shear stress versus shear rate information has been noted down. So, the curve, the data points are like this, and then we have drawn this curve. Now, you can see whatever the previous slide, the rheological behavior, whatever tau versus gamma dot yx are given, they are theoretically plotted, but true data you can see different forms may be have. You may not have a smooth curve in general like this in general. So, you may be having curve like this. Okay. But however, what you can see here there is a hysteresis only within this only up to, let us say, how much it is, approximately 700 seconds up to shear rate, approximately 700 second inverse, there is a time dependent behavior. After that there is no time dependent behavior. You can see both of them are almost constant value after 800 second inverse or something like that. Whereas now you take a 59 weight% solids red mud, then shear stress versus time. Now this is shear stress versus time it is showing. That means, apparent viscosity also shear stress versus apparent viscosity is shear stress divided by the shear rate, local shear stress divided by the corresponding shear rate. So if the shear stress is changing with time, that means apparent viscosity is also changing, right. So now this experiment we have done at different shear rates, right. 3.5 second inverse, 14 second inverse, 28 second inverse and 56 second inverse. So then what we can see, when the shear rate is low, the shear stress is sharply dropping down and then remaining almost constant, right. As you gradually increase the shear rate, what happens, shear stress versus time curve, this sharp drop whatever is there in the shear stress value at initial time of shearing, that is decreasing. So that means at the higher shear rates, whatever the time dependence behavior is there, that is also there only for the initial period of time only, that is very small. So for this material, what we understand here, that shear rate, the time dependent behavior is more significant if you are shearing at low shear rates, that is what you can see. If the material is not having any time dependent behavior, when you are shearing at a constant rate, you will be having a straight line, for the shear stress versus time curve. But now you are not having straight line, that straight line you are going to get after certain time only, but before that you can see there is a time dependence. The next type is rheopexy. So where apparent viscosity increases with the time of shearing if sheared at constant rate, and then examples are saturated polyesters, suspension of oleate, colloidal suspension of vanadium pentoxide, coal water slurries, gypsum paste, etc. So now if you take this saturated polyesters, now again shear stress versus time of shearing is data is provided, but this data has been conducted at different shear rates. So one is the 918.5 second inverse, like that gradually shear rate has been increased. Now what you can see here, when the shear rate is less than 1000 or even up to 1400 something like that, shear stress versus time of shearing curve, they are almost straight line. That means, up to 1500 or up to 1400 second inverse shear rate roughly, the material is showing a time independent behavior. But if you are doing shearing at further higher shear rate, then you can see the shear stress is increasing with increasing the duration of shearing. That means apparent viscosity is increasing, that you can clearly see. And then this increase is very steep, very significant, especially when you are doing the shearing at a very large shear rate values of order of 10 power 4 or something like that. So now in the previous slide, one example we have seen. Here in the case of thixotropy, what we have seen for red mud suspensions, the effect of time dependency behavior on rheology of the material is higher at lower shear rate, whereas in rheopexy, whatever the material that now we have taken here, the effect of time dependence behavior on rheology of this material is higher at higher shear rate, opposite trend we can see, and then it not necessarily be true for all the cases. So now we see models for time dependent non-Newtonian fluids. Actually there are not many models for the time dependent non-Newtonian fluids because of the dynamic nature of the material rheology. So getting such information and incorporating them in a proper model form, it is very difficult. So we have taken only one model, Hoska model for thixotropic behavior, which is having similar form like Herschel-Bulkley fluid model. Herschel-Bulkley fluid model, what we have? We have tau yx is equals to tau naught h plus m gamma dot yx power n, this form. So now when we talk about the Hoska model for thixotropic material, so then we have some addition here, and then we have some addition here, like that. The additions are corresponding to the time parameters. These tau naught h, m, n are with respect to the just without having any time behavior. When you have the time behavior, some additional parameters will come and join them. So that is what this model. It is a generalization of Herschel-Bulkley model by incorporating time dependent contribution. For a 1D simple shear flow of thixotropic fluids, it is given as tau yx is equals to tau y naught plus tau y1 plus m naught plus zeta m1 gamma dot yx power n. So, this tau y naught and then this m and this n are same as model parameter as in Herschel-Bulkley fluids, whereas this tau y 1 and then z and this m1 are corresponding to time dependent contribution, and then zeta whatever is there that gives the dynamic equilibrium between the for the material because of the time dependent nature. Okay. So, how it is, like we have d zeta by dt is equals to a 1 minus zeta minus b zeta gamma dot yx power epsilon, right. This is the build up of the structure and then this is the breakup of the structure. These two terms indicates build up of the structure because of the time dependent contribution, and then this gives the breakup of the structure because of the time dependent contribution. Okay. So, now tau y naught and m naught are yield stress and consistency index as in Herschel-Bulkley fluids. Tau y1 and m1 are time dependent contributions, and these are postulated to be linearly dependent on instantaneous structure, that is represented by the value of zeta. Instantaneous structure of the material is represented by this value zeta, right. So, that is how it is incorporating how the build up of the structure or breaking of the structure is has been brought into the equation number 2, that has been brought into the mathematical form by using this equation number 2. So, equation is valid for constant value of zeta obviously. So, the equation number 2 indicate rate of change of zeta, that is dynamic equilibrium between the rates of build up and then rates of breakdown of structure, correspondingly represented by the first term and then second term of this equation number 2 as I have shown in the previous slide. So, rate of breakdown depends on both the values of zeta and the value of shear rate as we have seen, whereas because that is having the term b gamma dot yx power epsilon, these terms are there. So, it depends on zeta as well as the gamma dot yx, that is shear rate also, whereas the rate of build up is having the term a 1 minus zeta. So, it is not dependent on the shear rate, but rate of build up depends only on the number of structural units available at any instant of time, that is the value of zeta. Okay. And then this model is very complicated because there are 8 parameters are existing: tau y naught, tau y1, m naught, m1, n, a, b, epsilon. So, this tau y naught, tau y1, m naught, m1, n are the material properties, whereas the a, b, epsilon are the kinetic parameters needs to be evaluated by experiments which are very cumbersome and very material to material. That is the primary drawback of this material. Okay. So, this is all about the time dependent non-Newtonian fluids. Now, we see the details of viscoelastic fluid behavior. Viscoelastic fluids examples, it is better to see how we see. So, we take two materials or two solutions, one which is not having any elastic behavior and then one which is having elastic behavior. So, the second one right hand side is viscoelastic material. We are stirring them now. When we are stirring them, so let us say in the left hand side, when there is no elastic behavior, the surface of the liquid that falls something like this. If you are rotating at higher speeds, then this may fall like this. If you are even rotating very high speed, something like this, so then you may even have the surface like this or something like this, right. All the fluid is being thrown towards the wall like this. That is the point to observe, wall of the container. Whereas, if the material having elastic behavior, so rather surface forming like this, it it climbs the rod like this. you can see the material is climbing the rod, steering rod, like whatever the steering rod is there, that that material is steering that rod, like this kind of thing that you can see in the viscoelastic material. Why it is happening, what are the reasons, that we are going to see anyway. Now, we will do one more experiment. So, here you take a solution which is not having elastic behavior. Okay, I am drawing the top view, and then you take a solution which is having a elastic behavior, right, like this. So, now what we do now, we try to rotate, right. So, now when you rotating like this, you can see the wrinkles. Let us say if you have some color solutions, etc. So, then you can see the wrinkles clearly, something like this from the top, right. So, when you stop the rotations, right. So, you can see all the wrinkles are stopped when there is no elastic behavior in the material. But if the material is having elastic behavior, so let us say you are rotating in a anti-clockwise direction like this. Right. Now, you rotate for some period of time, like few seconds or something like that, or few minutes, then you stop rotation. So, then what you can see, these wrinkles, whatever that you are moving in the anti-clockwise direction, even you stop rotating, they will be further moving forward, further slightly moving forward, then they will stop, then they will start moving in the clockwise direction. You rotated in the anti-clockwise direction. Now, you can see that these some wrinkles are something like they are moving like anti-clockwise direction. Why is it happening? Why is it happening? Because the material, whatever the viscoelastic material is there, the elastic nature, it is having the partial recovery, it is having some memory, so it is trying to go back to its initial position, right. So, that is one experiment. The another experiment that you can do, so you take a container in which you have a solution which is not having any elastic behavior. You take another container in which you take a solution which is having elastic behavior. Right. So, at the bottom there is a opening for both of the containers. Right. So, when the material you release from the container, in which you are taking a material which is not having any elastic nature. So, then you can see that material is flowing something like this. But the same thing if you do, you open the container from the bottom, the container in which you have taken the viscoelastic material. So, then you can see the material flows out something like this. A kind of swelling of this swelling behavior, you can see something like this. So, this is because of elastic nature, because the material is having elastic nature. So, why these are things happening? So, die swell, this is known as the die swell effect, and this is known as the rod climbing effect. So, these are primarily found because of the normal stress differences. These normal stress differences are in general found to be 0 for Newtonian fluids, but for the viscoelastic materials they are not 0. They are not 0 for the viscoelastic material. Because of these normal stress differences, the materials are showing different kind of behavior, and then this kind of normal stress difference which are not 0, that you find primarily in viscoelastic fluids, right. So, we see now some of these details, right now we see some of these details. So, this is about the viscoelastic fluid behavior, that is the material is having both viscous as well as the elastic nature. So, Perfect elastic solids try to regain its initial original form on removal of applied stress. When you apply a stress, external stress to the material which is elastic, so then it will undergo deformation, but when you remove that applied external stress, the material will try to come back to its initial position. If it is coming completely to its initial position, then we call them perfectly elastic solid material, right. But in the case of viscous Newtonian fluid, shear stress is proportional to shear rate, right. Once deformed, it will not come back to its initial position, whatever is the reason. Okay. Whatever may be the range of shear rate or shear stress applied, whatever the duration you applied, and then when you stop the external force, external stress, nothing is going to have a kind of influence. So, for viscous Newtonian fluid, shear stress is proportional to the shear rate, and then for such Newtonian fluids, coming back to their initial position even partially is not possible. So, but there are some material which display both elastic nature and then viscous nature as well, viscous flow nature as well. So, those material we call them viscoelastic materials. We call them viscoelastic materials. Two limits of viscoelastic materials are perfectly elastic deformation and perfectly viscous flow. So, obviously two limits are possible, and then that is material may behave like a viscous fluid on one situation and like an elastic solid in other situation, that is quite possible, that is what it mean by. Then viscoelastic materials have ability to store and recover the shear energy. The material is climbing along this rod of the stirrer. So, this is known as the Weissenberg effect of solution of polyisobutylene propylene. This is first reported by the scientist Weissenberg. Similarly, die swell. So, you can see the material when it is released, so then it is swelling slightly, right. So, this is die swell by a solution of 1% polyacrylamide in 50/50 mixture of glycerol and water. So, both of these effects whatever we have seen in these two pictures are there because of the normal stresses which are not 0 and their difference is also not 0. Okay. So, this is the first instance where people realized about non-zero normal stresses or their differences. Okay. So, that is the reason because of investigation by Weissenberg, this rod climbing effect is also known as the Weissenberg effect. So, normal stress in steady shearing flow is important in the case of viscoelastic material, that is what we realized, right. So, in simple 1D shearing motion, what you get in general, you get shear stress versus shear rate information only. But now, if the material is having elastic behavior, even in simple 1D shear motion, in addition to the shear stress, you will also have the normal stresses, and then their differences are going to play a role on the rheology of the material. Okay. Let us take 1D shearing motion of a viscoelastic fluid as shown here. So, now there are two plates are there. So, this is the one plate and then this is another plate, and then we are doing the shearing experiment either side like this. Whatever the fluid element that we have taken, let us say this fluid element we have taken between these two plates, right. So, if it is Newtonian fluid, you will be having only this shear stress tau Ix in general, because this is our x direction, this is our y direction, and then this is our z direction. So, we are taking 1D shearing motion. So, in case of material which is not having any elastic behavior, you will be having only tau Ix in the case of 1D shearing motion. But if the material is having elastic nature as well, so then you will be having this tau Ix, tau Yy and tau Zz also. Okay. So, that difference whatever the normal stresses, these normal stresses again they are having two components, isotropic pressure and then normal stress because of the viscous flow. Whatever the tau Xx, tau Yy, tau Zz are there, so they are the normal stresses because of the viscous flow. whatever because of the pressure, isotropic pressure, normal stress is there, that is P. Okay. So, this capital Pxx is having these two contributions. Similarly, capital Pyy is having these two contributions. Capital Pzz is having these two contributions, right. Fine. So, some books people write this sigma xx, sigma yy and then sigma zz also, right. Okay. So, now 3 normal stresses, that is Pxx or sigma xx, Pyy or sigma yy, Pzz or sigma zz along with the shear stress tau yx are possible if the material is having elastic nature even in 1D shearing motion like this, right. So, normal stress comprising of two components, that is isotropic pressure P and then contribution due to the flow. So, they are minus P plus tau xx is nothing but sigma xx. Similarly, sigma yy is nothing but minus P plus tau yy and then sigma zz is nothing but minus P plus tau zz. So, contribution due to the flow are known as the deviatoric normal stresses for the case of Newtonian fluids. They are known as deviatoric normal stresses for the Newtonian fluids, whereas they are known as the extra stresses for the case of non-Newtonian fluids. For the case of non-Newtonian fluids, whatever this tau xx, tau yy, tau zz are there, they are regarded as extra stresses. Whereas for the Newtonian fluids, they are regarded as normal stresses, deviatoric normal stresses. So, for Newtonian fluids actually this tau xx, tau yy, tau zz are 0, they are not having, they are individually 0, their difference is also 0. So, then P how you can define? You can, when you add these 3, sigma xx plus sigma yy plus sigma zz is equals to minus 3 P or P is equals to minus 1 by 3 sigma xx plus sigma yy plus sigma zz. Like this you can relate. But you cannot relate, you cannot have such kind of relation for this isotropic pressure in the case of viscoelastic materials, right. For non-Newtonian fluids, pressure cannot be defined as above as in the case of Newtonian fluids. For non-Newtonian fluids, differences of normal stresses are measured readily than individual stresses. We are going to see in the subsequent lectures how to measure the rheology of this material. So, there we can realize that measuring normal stress difference is quite easier compared to measuring individual normal stresses, right. Tau yy minus tau xx you can easily measure rather than measuring individually tau yy and then individually measuring tau xx. So, Weissenberg was the first one to observe that shearing motion of viscoelastic fluid gives rise to unequal normal stresses, and then that is causing the material to climb the rod while stirring this viscoelastic material, viscoelastic solution when you are stirring using a stirrer. So, then the material is climbing the rod because of this normal stress differences are not equal for those materials. So, obviously for a shearing flow of viscoelastic fluids, what are the information that you need to have? In general, if it is not having normal stress are not important, so then simply tau yx versus gamma dot yx information is sufficient. That is what we have seen for the time independent as well as time dependent fluids also. In time dependent fluids, additional term because of the dynamic equilibrium that d zeta by dt kind of terms have come. Otherwise, only tau versus gamma dot information only we are using till now. But now here, in addition to the tau versus gamma dot information, you need to have the first normal stress difference information and second normal stress difference N2 in addition to shear stress tau yx. So, in order to define a viscoelastic fluid, just having tau yx versus gamma dot yx information is not sufficient. You should also have N1 versus gamma dot yx and then N2 versus gamma dot yx information is also required. N1 is nothing but first normal stress difference, that is sigma xx minus sigma yy, and then N2 is nothing but second normal stress difference, that is sigma yy minus sigma zz, right. in the case of material which are not having elastic behavior, viscous material, so then we have the viscosity or apparent viscosity. So similarly, can we have something additional parameter here in the case of material which are having elastic behavior or not? So then we have this normal stress coefficients which are defined similar way, right. So normal stress coefficient, this n1 by gamma dot yx square is psi 1, and then n2 by gamma dot yx square is psi 2. The psi 1 and then psi 2 are nothing but the normal stress coefficients, right, which are like related to the first normal stress difference and then second normal stress difference respectively, right. So these are having units of Pascal second square, whereas the apparent viscosity is having Pascal second, because now here the stress difference, whether it is shear stress or the normal stress, the units are Pascals only, but it is being in apparent viscosity, shear stress is divided by the shear rate. So Pascal per Pascal divided by second inverse you are having, so then Pascal second. But now here the normal stress differences we are dividing by the square of the shear rate, so that is the reason Pascal second square we are having. Why are we doing this? Because when you plot this shear stress versus shear rate information, you can have a kind of you do not have any kind of limiting kind of conditions, but here n1 versus shear rate when you plot, so you can have a kind of limiting conditions which is having constant values. So that we will see in the next slides anyway. So let us not worry about that one. Rate of decrease of psi 1 with shear rate is greater than that of apparent viscosity. At what rate it is decreasing? Because of this square term here, and then at low shear rates n1 is expected to be proportional to the square of shear rate. That is the reason we are dividing n1 by square of the shear rate, so that to define this normal stress coefficients, or the psi 1 tends to have the constant value psi naught. Okay. At low shear rates, this n1 is expected to be proportional to the square of shear rate, that is the reason psi 1 tends to constant value psi naught. And then n1 by tau is a measure of degree of elastic behavior of a liquid, right. N1 by tau is a measure of degree of elastic behavior of the liquid. N1 by 2 tau is often used and called as the recoverable shear, in order to know whether the material is having any elastic behavior or not. Okay. N1 by 2 tau greater than 0.5 is also possible, and it is not at all uncommon. If it is N1 by 2 tau value is very much larger than 0.5, then we can say that material is very highly elastic in the nature. And then N1 versus gamma dot information is much less compared to the tau versus gamma dot information, available experimental data. So N2 versus gamma dot information even much less compared to N1 versus gamma dot, and then tau versus gamma dot information that is available, right. So N2 is also found is order of magnitude smaller than N1, and then it is negative. Sometimes it also changes the sign. Okay. So in the next class we will be discussing a few more details of the viscoelastic fluids, and then few problems on viscoelastic fluids. References for this particular lecture are provided here. Thank you.